Okay, so shall I start?
I will just introduce you in a minute now, and we can start. So, hi everyone, welcome to this Condensed Matter seminar, which today is receiving William Natori from Institute Landau-Laue in France, who is going to talk about local probes for edge states and topological 2D magnets. So, William, the stage will be yours. And if anyone has a question, you can unmute yourself, or you can just use the reactions button below and raise your hand. Then we can unmute yourself if you can. So thank you, William, for joining us and for accepting our invitation. Free you to start.
Okay, thanks a lot, Christia, for the invitation. And okay, this work, local probes for charge neutral edge states in two-dimensional quantum magnets, was a work I was doing while I was at Imperial College in London and receiving a grant from this Newton International Fellowship. Right now I'm at Institute Laue-Langevin in Grenoble, and this work, of course, couldn't be done only by me, so I have to give many thanks to Johannes, who was both my supervisor while I was in London and is now a professor at Technische Universität München, as well as to Professor Michael Knapp and his PhD student, Johannes Feldmayer. So while I was organizing my lecture, I figured out that I was doing one of the seminars that were destined both for a bit for experts, but also for non-experts. So I had to give a lot of background, and many people could just get lost. So just one slide to summarize what the result is that we investigated spin-polarized STM as a probe to topological magnetic edge states. And we tried to find what is the direct relationship between the tunneling conductance that we measure here in STM at different points of when we place the chip in different points of the magnetic material. The goal, to give a more precise goal, we try to see what would be the response of the edge states of the chiral spin liquid phase in the Kitaev model when it's subject to a magnetic field. And we indeed find some differences between the response in the bulk of the material, which is this black curve, in relation to what we find in the edge of the material, which is this red and the blue curves. And we can, in principle, find these different correlations on the borders of the material just by changing the relative polarization, spin polarization between the chip and the metallic substrate upon which we are placing the magnet. So let me now start talking the most general way possible about reductionism and emergence in general. So let me quote by one thing of an illustration of this London-based philosopher, Sir Roger Scruton, who unfortunately passed away last year. And he claims that if you want to know what emergence is, you have to think of paintings. So a painting is certainly an object that is composed by blobs of paint. And you can actually make a pixel by pixel analysis of this photo here. Otherwise, you couldn't see it on your screen. However, there are elements of a painting that are never that are formed by coherent arrangements of paint and cannot be reduced just to individual blobs. And this is more well seen if you go to modern art and find pictures like these that are basically just paint and figure out that they lack properties such as lines, shadow, shape, composition, or perspective, which are the emergent properties in arts. Philosophers normally use this language that the painting supervenes on the blobs of paint. Now, this is actually a similar the relation that we see in condensed matter physics when we think about condensed matter systems in its relation to the atoms that compose them. So condensed matter systems always supervene on atoms. Regardless the system, the dimension, or the property we are measuring, we are always looking to things that are there only because there are atoms forming the system, but they cannot be reduced to the atoms. The prime example of a property like this are phases of matter, which are never well defined for few atom systems, but they depend on statistically defined properties for many, but in many body systems. So in classical statistical mechanics, we consider that emergent processes, the emergent phenomena that occur by the cumulative effects that are protected by symmetry. And these are the ones that lead to microscopically discernible phenomena that you can measure with our probes. But there are now some trends in this, what has been now called quantum materials, which is the focus of these seminars, which are emergent phenomena in which this macroscopic behavior requires the use of a quantum terminology in order to be explained. And I'm sorry that my PowerPoint is actually doing this automatically transition, but let me just move on and focus on a specific kind of quantum materials, which are those that happen that occurs in magnetic systems. So if you just, for an illustration, you draw this axis of quantumness, in one extreme, you have to think of something that's very classical, such as the Ising ferromagnet, which has only this ground state that is defined as a project state of spins. It has only the Z2 symmetry, and the excitations are just spin flips that are +1 or -1. If you go to something a bit more sophisticated, you can think of the Heisenberg ferromagnet, and it's something similar in the sense that the ground state can still be thought of as a project state. But now, thanks to the SU2 symmetry of the spins, you have a continuous way to vary the spins instead of only the Z2 transformation. And the excitations are now written in terms of spin waves, which are defined in terms of, which are described in terms of bosons. So in this sense, this ordered state is semi-classical because, well, you already need to consider some statistics here by saying they are bosons. A quantum spin liquid would be what we call a totally quantum system in a magnetic material. And it's well exemplified by the Kitaev model. In the Kitaev model, you have Ising interactions, just like in this Ising ferromagnet. but it's in a different way, because now you have ice interactions as Z on these blue bonds, SX on the green bonds, and SY on the red bonds. This model turns out to be exactly solvable, and the ground state cannot be written in terms of a simple project stage, but rather you have to map it into a free Fermi problem, which will be characterized by a Z2 gauge field that's static and Majorana fermions. So the excitations will be these visons, which are alterations of the Z2 gauge fluxes, and the Majorana fermions. Well, much of the continuous interest in this model, it's because it turns out to be relevant to describe the magnetism of a class of materials. You can see this seminal paper from Jacqueline Caliulin, a PRL from 2009, in which they describe how this Kitaev physics would arise in a 4G5 or 5G5 based Mott insulators. So the key here is you have to keep the orbital degeneracy, and the ion should be heavy enough so that you can justify a description in terms of this total angular momentum 1/2. If you want a honeycomb lattice, just like I showed before, you have to arrange the octahedral in this manner, in which the metal ligand metal paths form this 90 degrees angle. And in this case, you will see that the hopping allowed by symmetry will be orbitally dependent and also directionally dependent. So if you just do the same derivation of minimal models using second order perturbation theory, and to start, you just consider the case in which only this hopping matrix T2 is not zero, you will find out that the minimal model is exactly the Kitaev model. So there are now several examples of materials that were synthesized following these Jacqueline-Caliulin prescriptions. The one that I will focus in this seminar will be this one, ruthenium trichloride. This material does not display a quantum spin liquid ground state, but rather the zigzag antiferromagnetic order. But that's not a problem, because if you instead consider all these hopping matrix, all these hopping parameters, you will derive this model here, the so-called JK gamma gamma prime model. And this model turns out to stabilize this phase. So it's actually explained by the theory developed by Jacqueline Caliulin in some sense. So one of the things that are interesting of Kitaev materials is that they can be a gateway to all emergent phenomena in magnetism. So again, the axis of quantumness, of course, it will host a quantum spin liquid. Something that's less discussed because people think it's less interesting is that it always hosts a Eisen ferromagnet. You just have to set the Kitaev interaction to 0 and set all the other parameters here equal to one another. And also one of the, and of course, it will host a lot of different classical orders that will have, will be described by spin wave theory, whose excitations will be described with the spin wave theory. So yeah, you can in principle have all the all magnetism in this simple model. It's kind of simple model, not too simple actually, but a physically relevant model. So, and also one thing that's interesting is that in this ruthenium trichloride, although it is an ordered material when you consider its ground state, if you apply a magnetic field between 7 and 9 Tesla, you will find that the order vanishes. And this is actually seen in this time-of-flight neutron scattering experiment. These circles here in green, they are pointing to this M point that corresponds to the order of the zigzag phase. And you see that it progressively vanishes as we apply a magnetic field on the honeycomb plane, up until this 8 Tesla picture in which there is no longer any sign of order. So people are very interested in this onset of a disordered state due to magnetic field, but people still don't know if this is a quantum spin liquid or if it's a state with multi-magnum excitations that are incoherent. So this is still an open question, and nobody can just simply claim it's a quantum spin liquid, but it's something that really deserves to be investigated. So we need to use this we used this to motivate the search for a smoking gun signature of this Kitaev spin liquid. Now, so let me now start with the technical stuff. And also something that's interesting to introduce general Kitaev physics. So one thing that's interesting is that neutron scattering response of the Kitaev model can be exactly calculated. And this is much to this fact that every eigenstate of the Kitaev model displays ultra-short correlations. So that means all correlations will vanish beyond nearest neighbors. And moreover, these correlations will actually be non-zero only for specific directions. So only correlations between SZs, the spin SZ, will occur along this blue bond, only along SX correlations along these green bonds, only SY correlations along these red bonds. So, and this matrix element here, you can show that you can map it to a quantum quench problem in which you consider the effect of acting a Majorana fermion, then applying a modified Hamiltonian, the evolution operator of a modified Hamiltonian with these two extra fluxes, apply another Majorana, and then return back to this to the Hamiltonian of the ground stage. This matrix element here, you can show that it can be written in the form of a certain functional integral. And since this functional integral is of a problem of Majorana fermions, it actually can be calculated in terms of a Pfaffian of a large real space system. And if you just calculate the fathing of this system, you will find this correlation in real time. Then you do the Fourier transforms and find the dynamical structure factor, which is the quantity that you will normally observe in neutron scattering. You can have more details of this in these classic papers from Johannes Knoll. Now, what's interesting of this is that even if you consider the ground stage of the ruthenium trichloride, you will find some high energy excitations that are consistent with these neutron scattering experiments. But let me just pass on to the next part, which is even more interesting. It was actually proposed by Kitaev himself in his original paper. So the idea is that if you act with this magnetic field perturbatively on the ground state sector of the Kitaev model, you will find that effectively the magnetic field will induce a three-spin interaction. And this three-spin term does not break the integrability of the model and also corresponds to a hopping between second nearest neighbors with a certain with this certain pattern here. So that's very close to this Haldane model. Now, this next nearest neighbor hoppings also actually induce a gap opening if you apply them to the gapless phase of the Kitaev model. And this gap opening is a topological phase transition that's characterized by this integral number nu, which corresponds, which says if there are edge states and if these edge states are clockwise or anti-clockwise rotating. And these edge states will carry energy, so heat energy, and you can find what this energy is using first just this integral that you can calculate using solid state formulas, but also this other more sophisticated formula that Kitaev provides in his paper using conformal field theory, in which the thermal Hall conductivity I here is related to this pi over 12 t squared term times this C minus, and this C minus is actually that tells that the thermal conductivity has a fractional quantized character. So this C minus would be Ni over 2. And most interestingly, okay, yeah. Okay, most interestingly, the experiment was done in ruthenium trichloride, in which you apply a magnetic field to the sample, and the sample and measure the thermal conductivity on here on the borders, and you find that this line here corresponds to the C minus terms, and they found equal to 1/2 for different configurations. So this paper from Kasahara and others would each correspond to the first signature of fractional quantization since the fractional quantum Hall effect. Again, there is still no confirmation of this, but this is interesting. So the question, of course, is how can we ensure this is a signature of a topological edge state of a chiral Kitaev spin liquid? And what we desire is something that already exists for charged topological states of matter. such as in ARPs for topological insulators or topological superconductors, in which you can gradually compare the spectral function that you calculate theoretically with the results of the experiments. So Johannes gave this idea that perhaps spin-polarized scanning tunneling microscopy could be used as a spectroscopic probe for quantum spin liquids, and that this could have the advantage over neutron scattering, that we could measure the correlation functions locally instead of just taking them in the reciprocal space. So here's the physical system, and oh my God, I don't know what's happening with my slides, but here's the Hamiltonian, and the Hamiltonian will have the chip, of course, the HE, there will be metallic substrate, and you use your magnet as the insulating the insulating material that lies between the chip and the substrate. So there will be a tunneling current between this metal here and the metal here. But the key point is that the electrons will have to tunnel through your magnet. So when they do this, they will interact with the magnet itself, and part of this interaction will be magnetic itself. So part of them will have these Heisenberg interactions between the electrons of the substrate and the electrons in your magnet. And the current itself will depend upon how the spins will be, the relative polarization of the spins in the chip in the sample. And if you just do some calculation of what would be the current using Fermi-Golden rule, and then derive in relation to the difference of potential that you apply between the chip and the substrate, you'll find this formula here, which will depend on the C alpha beta factor that corresponds to the relative polarization of the spins, and the dynamical structure factor, which is local here. And this is the one that we calculated with in that neutron scattering studies. One technical detail is that since we are interested in edge states, we have to do all computations in the real space. And in this case, if you want to have something exact, the Pfaffian approach is the best approach to calculate these dynamical structure factors. So that's why we introduced these then rather than other techniques. So, okay. As a test, we of course used the Kitaev Hamiltonian with the 3-spin term. And we considered the case in which the Kitaev couplings are isotropic, and the kappa is 0.2 of the times J. So one thing about the STM is that you can move the probe around your sample. So we could calculate, let me see if I can, okay. No, I can't. So, so we can calculate what is the response in the bulk, which is position B here. And if you go to the bulk, you will find that the larger response will be due to the excitation of those Z2 fluxes, and there, which are these things here in purple. If you go to the edges, there are two different behaviors that you can find. So if you consider the broken bond, you will have this wavy line here, which shows some coupling to the magnetic edge states. In these broken bonds, you actually find that the energy of these flux excitations goes to zero. So that's why you don't have something like this great peak in black. But if you go consider unbroken bonds, such as the X bond, you will have some correlation that will you will also excite one flux here in this side of the sample, and there will be a half of the excitation of half of the Wison gap here, plus something else that's qualitatively similar to the bulk. So you can return to that formula for the tunneling conductivity. Just plug in these dynamical correlation functions that we measure. And then you can tell the experimentalists that if they can just polarize both the spin on the chip and the spin on the metallic substrate. And this will give the different, this will allow you to measure different correlation functions. So if you polarize the chip and the substrate with the same spin, you will measure just the SZ correlation, which will give the response of these edge states. And if you polarize with the opposite in the opposite directions, you will measure the correlations of everything but this SZ correlation. So you will find something closer to this red line here. That's in both cases, you have something that's different from the bulk, and this reflects the different kind of excitations that you find on the borders and on the bulk. So to conclude, I discussed this spin-polarized scanning tunneling microscope as a potential probe for topological edge states in quantum magnets. We showed how tunneling the electrical potential and the spin polarization can be used to detect chiral edge states in Kitaev spin liquids. And this is actually part of a larger ongoing effort to probe quantum spin liquids with electrical probes. So we're all hoping that there will be experimentalists trying to do something more concrete with these theories we're developing right now. Some future directions. Well, besides this magnetic field, this induced quantum spin liquid through magnetic fields, there is another proposal that is the Kitaev model can be tuned into this ruthenium trichloride by placing some strain that changes this angle of this metal ligand metal angle theta here. Because if you go to a certain region, you will find that this Kitaev interaction in black here dominates strongly over other interactions in this JK gamma prime model. So this idea was tried to be implemented through pressure, but it didn't work. It leads to a valence bond phase. But if you just place ruthenium trichloride over on graphene, you'll find that this system by proximity effects leads to some doping, and this doping leads to some strain. And if you see this table that considered recalculated the minimal model with using ab initio methods, they realized that the Kitaev interaction rises while the Heisenberg interaction reduces in this system by just placing it on graphene. So the question is it a way of having this Kitaev spin liquid? There is one experiment that was done, and in this device here, using graphene over ruthenium trichloride, and they tried to measure the quantum oscillations in graphene. So they used this simple model, simplified model of a Kitaev plus a Kondo coupling model. And they found out that there are some agreement between a mean field theory that considers the hybridization of these graphene electrons with fractionalized excitations in quantum oscillations. I actually am not involved with this project, so I don't know much of the details, but this seems to be very interesting, and it's also a system which already corresponds to this setting for the STM probes, right? You have a metal, the graphene, and then over it you have a ruthenium trichloride. So this is a system that could be investigated with spin-polarized scanning tunneling microscopes in principle. So with that, I think I have said everything I have to say. So many thanks.
Thank you very much, William. Now we have time for questions. So everyone who has a question, feel free to unmute yourself and ask, or type it here in the chat box. Well, nobody asks. I have a question. Noah has a question.
Great talk. My name is Noah Brayali.
Hey,
great talk. I'm thinking about the Jackley-Kalaluen paper that you referenced. And I recall that George also looked at the iridates that have a similar configuration, if they're 5D rather than 4D. And for sodium iridate, it has these edge-sharing octahedra, as I recall. It's a
yes.
It's 4+ with the J effective half. And there was some tunneling done on it by the Kentucky group, Gang Chao's old group, about maybe 10 years ago now. And they also Gegenwart's group in Germany. And I wonder if you thought at all about the iridates in the context of your calculations for doing tunneling to measure the structure factor. Just as a note, we looked at the 214 iridate that has the similar setup, but it's corner sharing octahedra. It's a mod insulator with a Heisenberg dominates. And we saw some mid-gap states, because the main thing you see is the Mott gap. But we saw these mid-gap states that we interpreted in exactly the way that your calculation interprets that. You see it as a step, at the the Heisenberg coupling. You call it, in the Kitaev case, it'd be the Vizon gap.
Okay. Well, the theory, of course, we were thinking using this ruthenium trichloride as a motivation, because this is the one that showed some signature of quantum spin liquid physics. As far as I know, this was not found in iridates, except this one based in hydrogen, right? In which you have something like a disordered Kitaev quantum spin liquid. So in terms of motivation, we didn't consider, we didn't think of actually any material in principle. Because if we want to be realistic with these Ari dates, I think what we should do is to replace this model here, this Hamiltonian, from this Kitaev model to the general JK gamma gamma prime model, and then then expand it in terms of spin waves and calculate the response you would expect using spin waves.
Yeah, that's what we did for 214. For 213, it has this honeycomb structure and the zigzag antiferromagnetic order at 20 Kelvin. So 20 Kelvin is like nothing compared to J. J is like 100 MeV, it's like 1,000 Kelvin. So it's a similar kind of thing that, yeah, you know, these materials always conspire to be semi-classical, right? And but if we apply a magnetic field to sodium iridate or something, maybe put it on graphene, a thin film, maybe it'll do the same as this ruthenium.
Yeah, maybe. I don't know about it. Maybe something that one could ask to Rosa Valenti or so. But yeah, I don't know if for this honeycomb iridates, I think the best route to quantum spin liquids is really ruthenium trichloride and this hydrogen-based lithium iridate. But yeah. But thanks for the question.
Other question? I have a question. In the results you showed for the differential, the current differentiated with respect to the tensor, the set looks like there is some plateau. So does it happen to be quantized or?
The plateau. Okay. This is actually one thing that's interesting about the Kitaev model. If you consider just the dynamical structure factor, let me do something kind of unusual. And you see, therefore, you will see that the dynamical response will always have a small gap here. Not really small, but something like 0.26 times the Kitaev coupling in the isotropic limit. And this is even if the Majorana fermions are gapless, okay? So, and that's because the first response of your spins, of the spin correlation is the formation of this Weisung here. And these Weisums are always gap excitations. So this bump in the response of the tunneling conductivity, it's just reflecting this, it's just reflecting the formation of these Weisung gaps. It's quantum, but it's not really quantized in these things.
Thank you. Questions? More questions? Any comment?
Oh.
Comment on step.
Comment on step. Well, let's see. Do you mean that there is this step here that's on the bulk? Well, if you go to again to the original Kitaev, you will see that the strongest response is due to exactly this bump here, and then to the formation of these Z2 gauge fluxes. And then it will decay fast and will not be very, very big, right? So the tunneling conductivity, if you just go back to the formula, will be an integral of this correlation, dynamical correlation function And then you will see that, yeah, it will be a normal step function because of this.
I think Chris's comment or question was, so what do you have to do to see a peak? And I guess the answer is to take a derivative of di dv. So you look at the d squared di dv. It's a typical thing in inelastic tunneling, that once you pass the threshold, then you can start to see the signal in the electron tunneling. And so rather than a peak, you see a step, because it's the integral of a delta function.
Yeah, that's true. You could use this as a probe of some Kitaev spin liquid in your system. That's true. The second derivative.
More questions?
Yeah. I'm seeing a lot of people from the University of São Paulo here.
Yeah.
Anyway.
All right, so if you don't have any questions, let's thank William again. Thank you very much for being with us, William, and hope to see you all next week.
Okay, thanks
Bye.
a lot. Bye.